Look up at the night sky for a moment. Every star you see is a massive nuclear engine burning for millions or billions of years. But hidden among those distant lights is one of the universe's most terrifying secrets. Some stars don't simply die, they collapse into black holes. Imagine a star so massive that when its life ends, gravity crushes it into a region where even light cannot escape. No surface, no glow, no direct way to see it, just a cosmic abyss that bends space and time itself. And yet, these invisible objects are scattered throughout the universe. Some even lurk at the centers of entire galaxies. So here's the mystery. Why do only certain stars end their lives this way? What transforms an ordinary star into one of the most extreme objects in existence? And what actually happens during the terrifying moment when a star collapses? To answer that, we'll travel from the microscopic reactions inside a star's core, to the explosive deaths of massive stars, to the giant black holes shaping entire galaxies. Because the story of black holes isn't just about death, it's about how the universe builds its most powerful structures. Out there in the vast darkness of space, stars live long and dramatic lives. For millions or even billions of years, they shine steadily, lighting up their cosmic neighborhoods. Yet when their lives finally reach the end, not all stars share the same fate. Some fade quietly, while others collapse into something far more mysterious. Imagine a star as a colossal cosmic engine. Deep inside its core, unimaginable heat and pressure keep everything running. This energy pushes outward, holding the star up against its own crushing gravity. It's a delicate balance, like a tug-of-war that can last billions of years. But sooner or later, the fuel begins to run out. And when that happens, gravity starts to gain the upper hand. The star's core begins to shrink, pulling matter inward with terrifying force. In some stars, this collapse leads to one of the most extreme objects in the universe, a black hole, a place where gravity becomes so powerful that even light can't escape. No surface, no glow, no direct view, only a region where space itself bends inward. It's as if the universe carved out a doorway into the unknown. But here's the puzzle that keeps astronomers awake at night. Why do only certain stars end their lives this way? Why does one star quietly fade away, while another collapses into a cosmic abyss? To answer that, scientists first had to learn how to detect something that cannot be seen. At first glance, black holes seem impossible to study. After all, how do you observe something that emits no light at all? For decades, this question puzzled astronomers scanning the skies. Yet the universe, as it turns out, leaves clues everywhere. One of the earliest hints comes from the motion of stars. Sometimes astronomers observe a star orbiting something invisible. It moves in a tight circle, as if tethered to an unseen anchor in space. The only explanation is a massive object lurking in the darkness. It's a bit like watching leaves swirl in a whirlpool. Even if you can't see the water beneath, the motion reveals the hidden force. In the same way, the dance of stars betrays the presence of black holes. Gravity leaves fingerprints, even when the source itself is hidden. Another clue appears when matter falls toward these invisible giants. Gas and dust spiral inward, forming a blazing disk around the black hole. As the material spins faster and faster, like an ice skater pulling in their arms, it heats up enormously. This glowing whirlpool releases intense bursts of X-rays into space. And then there are the most dramatic signals of all. When two black holes collide, they shake the fabric of space itself. These ripples, known as gravitational waves, travel across the universe like cosmic echoes. Through them, scientists realized something astonishing. Black holes aren't rare at all. They're everywhere. To understand why some stars collapse into black holes, the journey must begin in a place no telescope can see. Not in galaxies, not in stars themselves, but inside the tiniest interactions of matter. Deep within a star's core, atoms are colliding billions of times every second. And in those collisions, the true engine of a star is born. At the center of a star, temperatures soar to millions of degrees. Under such extreme conditions, atoms move so violently that they smash together. When this happens, lighter elements fuse into heavier ones, releasing enormous energy. This process is called nuclear fusion, and it's the reason stars shine. The energy from fusion acts like an outward pressure. Imagine blowing air into a balloon while someone tries to squeeze it shut. The air pushes outward while the hands push inward. A star lives in the same cosmic balance between energy and gravity. Gravity constantly tries to crush the star inward, but fusion pushes back, keeping the star stable for millions or billions of years. As long as this balance continues, the star shines steadily in the darkness. It's like a spinning top that stays upright as long as it keeps moving. But here's where things begin to change. Fusion can't last forever. Eventually, the star runs out of fuel. When the microscopic reactions inside the core slow down, the outward push weakens, and that's when gravity begins preparing something far more dramatic. Now the story expands from the tiny reactions inside atoms to the immense pull of gravity itself. Gravity is one of the most familiar forces in our daily lives. It keeps our feet on the ground and the oceans tied to Earth. Yet in the universe, gravity can grow unimaginably powerful. Every massive object creates a gravitational pull. Planets pull on moons, stars pull on planets, and galaxies pull on billions of stars at once. The more mass an object has, the stronger its gravitational grip becomes. It's like a cosmic magnet, drawing everything toward its center. Think about how the moon orbits Earth. Earth's gravity constantly pulls the moon inward, but the moon's motion keeps it circling instead of crashing down. This graceful dance happens everywhere across the universe. Inside stars, however, gravity plays a much more intense role. The enormous mass of a star squeezes its core from all directions. This pressure becomes so strong that atoms are forced closer and closer together. In fact, this crushing force is what allows nuclear fusion to begin in the first place. But not all stars carry the same weight in this cosmic struggle. Some are relatively small, like our Sun. Others are giants, containing many times more mass. And those heavier stars are the ones where gravity may eventually push things to the extreme. Studying black holes might sound like trying to investigate a shadow in the dark. After all, these objects hide themselves from direct view. Yet scientists have become remarkably good at tracking their presence. They do it by watching how the universe behaves around them. Space telescopes constantly scan the cosmos for unusual signals. When matter spirals toward a black hole, it heats up and shines intensely. This glowing disk of gas can become one of the brightest objects in a galaxy. From millions of light years away, telescopes detect this radiation. It's a bit like watching sparks fly when metal grinds against metal. You may not see the machine inside, but the sparks reveal something powerful at work. In the same way, radiation from falling gas exposes the hidden monster nearby. The brighter and hotter the disk, the stronger the gravity pulling it inward. But telescopes aren't the only tools scientists use. On Earth, enormous observatories listen for vibrations in space-time itself. These instruments detect gravitational waves, tiny ripples traveling across the universe. They form when massive objects like black holes collide. When those ripples reach Earth, detectors register faint signals passing through our planet. It's like hearing a distant drumbeat echo across cosmic space. From those signals, scientists can calculate the masses and motion of black holes, and these discoveries reveal something crucial about how such extreme objects are born. At the heart of every star lies a fragile cosmic balance. On one side, gravity pulls everything inward with relentless force. On the other, nuclear fusion pushes outward, releasing enormous energy. As long as these forces remain equal, the star remains stable. It's a bit like two teams in a tug-of-war. Gravity is constantly trying to drag the star's matter toward the center. Fusion pushes back, generating pressure that holds the star up. For most of a star's life, neither side wins, but eventually the fuel begins to run out. The nuclear reactions slow, and the outward pressure weakens. Gravity, however, never stops pulling inward, and when that balance finally breaks, the collapse begins. Imagine removing the air from a balloon while someone keeps squeezing it. Without the pressure pushing outward, the balloon shrivels instantly. In a star, something similar happens when fusion shuts down. The core suddenly finds itself defenseless against gravity. For smaller stars, the collapse eventually stabilizes into dense remnants. But in the most massive stars, gravity pushes far beyond those limits. The core compresses more and more, shrinking into an incredibly tiny region. And that unstoppable collapse sets the stage for one of the universe's most extreme transformations. Long before a star ever collapses, its life begins in a quiet region of space. Vast clouds of gas and dust drift through galaxies for millions of years. At first, they seem calm and motionless in the darkness. But gravity is already at work, slowly pulling the cloud inward. As the cloud contracts, it begins to spin faster and faster. It's similar to an ice skater pulling their arms inward during a spin. The shrinking cloud rotates more quickly, flattening into a swirling disk. At the center of that disk, a newborn star ignites. Once nuclear fusion begins, the young star lights up its surroundings. The leftover gas and dust in the disk start clumping together. Tiny particles stick, forming rocks, then larger bodies, then planets. This is how solar systems, like our own, are born. Our sun formed in exactly this way about 4.6 billion years ago. Around it, the planets slowly assembled from the remaining material. Earth, Mars, Jupiter, and the rest are products of that ancient disk. They orbit the sun in the same orderly motion that began long ago. But while stars may be born in similar ways, their endings can differ dramatically. Many stars end their lives quietly, leaving behind dense stellar remnants. Yet the most massive stars follow a far more violent path. And when those giants collapse, the consequences echo across the entire cosmos. When massive stars reach the end of their lives, the universe witnesses one of its most spectacular events. Before collapsing into black holes, many of these stars explode in colossal supernovae. For a brief moment, the dying star can outshine an entire galaxy. It's a cosmic finale that sends shockwaves racing through space. But this explosion isn't just destruction, it's also creation. Inside stars, nuclear fusion forms heavier and heavier elements over time. Yet the heaviest elements require the extreme conditions of a supernova to exist. Only in that violent blast can atoms like gold, uranium, and platinum be forged. Once the star explodes, those newly formed elements scatter across space. They mix with clouds of gas and dust drifting through galaxies. Over millions of years, these enriched clouds collapse again to form new stars and planets. The universe, in a sense, recycles the remains of ancient stars. Our own planet carries the legacy of these stellar explosions. The iron in Earth's core, the calcium in our bones, even the oxygen we breathe. All of these atoms were forged in the hearts of stars long before the sun existed. Every element around us has traveled a cosmic journey across billions of years. So when massive stars collapse and form black holes, they also reshape the future of galaxies. Their explosions spread the ingredients needed for new worlds and life itself. In a strange way, the death of stars becomes the birthplace of planets like Earth, and that connection leads us to an even larger stage in the universe. Zooming out even farther, black holes are not just isolated remnants of dying stars. Across entire galaxies, these mysterious objects appear again and again. Astronomers have discovered that many galaxies hide enormous black holes at their centers. These giants are millions or even billions of times heavier than our sun. At the heart of our own galaxy lies such an object. Stars near the center of the Milky Way race through space at incredible speeds. They orbit an invisible point, completing their paths in just a few years. Something incredibly massive must be pulling them inward. It's a bit like watching planets orbit the sun. Even without touching the sun, the planets follow its gravitational command. Near a galactic center, stars follow a similar pattern. Their motion reveals the presence of a colossal black hole. These supermassive black holes can shape entire galaxies. As gas falls toward them, enormous jets of energy can blast outward. These jets can stretch thousands of light years into space. They influence how stars form and how galaxies grow. So black holes are not just the endpoints of dying stars. They are also central engines in the architecture of galaxies. From stellar collapse to galactic structure, gravity's reach grows ever larger. And to fully understand this cosmic story, we must travel back to the very beginning of the universe. To truly understand black holes, the journey must stretch all the way back to the beginning of the universe. Nearly 13.8 billion years ago, the cosmos emerged from an unimaginably hot and dense state. In the early moments after the Big Bang, the universe contained only the simplest elements. Hydrogen and helium drifted through space in vast, dark clouds. For millions of years, the universe had no stars at all. It was a quiet, dark expanse filled with slowly cooling gas. But gravity, patient and relentless, began pulling matter together. Gradually, the first stars ignited in the young cosmos. These earliest stars were very different from the ones we see today. Many were enormous, far more massive than our sun. Their immense gravity crushed their cores to extreme conditions. They burned their fuel quickly and lived short, brilliant lives. When these giants reached the end of their lives, their collapse was catastrophic. Some exploded in powerful supernovae that enriched the universe with heavier elements. Others collapsed directly into black holes, leaving behind invisible gravitational anchors. These early black holes may have helped shape the first galaxies. Over billions of years, galaxies grew and evolved around these structures. Stars formed, died, and recycled their material again and again. Black holes continued to appear as both stellar remnants and galactic giants, and all of it traces back to those first moments when the universe began forming stars. Across the universe, gravity writes some of the most dramatic stories in existence. From the gentle pull that guides planets around stars to the crushing force that collapses entire suns, gravity quietly shapes the architecture of the cosmos. When a massive star collapses into a black hole, the transformation is almost unimaginable. Matter compresses beyond ordinary limits, space bends inward like a whirlpool, and time itself begins to behave in strange ways. These objects represent one of the most extreme outcomes nature can produce. A star that once lit its surroundings for millions of years can become an invisible region where the familiar rules of space and time twist. It's destruction on a cosmic scale, but also a doorway to deeper mysteries. Because black holes are more than just endpoints of stellar life. They challenge our understanding of physics itself. Inside them, gravity becomes so powerful that our current theories begin to break down. It's as if the universe is hiding secrets just beyond the edge of the event horizon. And perhaps that's the most fascinating part of all. The same universe that creates stars, planets, and life also produces these enigmatic regions where reality bends to its limits. Black holes remind us that even in cosmic endings, the universe still invites us to keep exploring.